First thing we're going to go over are some statistics fundamentals in R. And this isn't necessarily specific to multivariate analysis, but it's a helpful thing to begin with just to practice doing some of the basic stats work that we've learned before in R. So we're going to look at a data set that was collected during a study that was done here at Fordham. And the study was looking at whether people would rather take advice from human experts or statistical algorithms when making predictions about the future. And there were a couple different factors, including how long into the future the subject was, or the event was, as well as the subject that was being forecasted. So there were some questions were about economics and some were about politics. And so we can get a quick snapshot of our data by just looking at the first 6 rows using the head function. Oh, and just as a refresher, when we're loading our data, a lot of times what we want to do is start with this rm list equals ls command. What this does is clears out our working environment, so there's not extra stuff floating around in there. Then we need to set our working directory to the location where the data that we're going to be using is. And note that these are forward slashes, not backslashes. So if you copy from Windows or something like that, you may need to switch them to backslashes, which you can do with the find and replace function. And then this data is in CSV format, so we can use the read.csv function to load up our data. And then we just name it an object. In this case, I name it DAT, which is sort of a common convention that you see in R. So again, we can look at the first 6 rows of our data by calling the head function on our data object. And so we see we have several variables. So the key variable that we're going to be interested in is this RESP variable. This goes from 0 to 100, where lower values mean people prefer human advice, and higher values mean people prefer algorithmic advice. But there are several other variables, including, so month is how far into the future the event was, September was short, November was long. So September was about 2 weeks and November was about 8 weeks. And then the domain is the subject being forecasted, and then there's some information about each subject here. So again, here is a little bit about our variables. We can look at the variable names by calling call names, which gives us the names of each variable in our data set. So once again, ID is a participant ID, month is how far into the future the item looks, domain is the subject, and then some other relevant variables are stats classes, which is how many statistics classes the participant has taken, and then RESP is the variable of interest, which is whether they prefer machine advice, which is high values, or human advice, low values. So we can check the correlations between 2 variables using the COR function. And here we use the $sign to call variables from within our data set. So this is just a quick way to look at individual columns from your data. You do name of the data object, $sign, and the variable you're interested in. So we're checking the correlation here between age and the number of stats classes people have taken. We see that this is negative. So the older people are, the fewer stats classes they've taken, but it's a pretty weak negative correlation. You can also get full correlation matrices by calling the core function on a data frame or matrix, as long as every variable is numeric. So here I'm using the square brackets to just subset the data to these 3 variables. You can always do this with any data set. And so this is a correlation matrix between age, stats classes, and the RESP variable. So you see this outputs a full matrix with 1s along the diagonal, just like any correlation matrix, and then the correlations off the diagonal. And another neat thing we can do is we can nest this inside of the round function. So here you see inside the round function, we have the exact same thing as on the previous page here. And then I just put it inside of round, and I specify that I want to round to 2 digits, and this just makes everything more readable. Just rounds everything off to 2 digits. We can test the null hypothesis of the correlation equals 0 on a particular correlation using the core test function. And so you see this is gives us quite a bit more information. It does give us our correlation down here at the bottom. It gives us a 95% confidence interval, as well as a test statistic, degrees of freedom, and a p-value. So here we see age and preference for algorithmic advice, or machine advice, is actually significant. So it's a negative correlation, and p less than 0.05. So the older people are, the more they prefer human advice as opposed to algorithmic advice. We can also conduct t-tests with the t.test function. And so the default when we do this is a Welch's two-sample t-test, which means we're not assuming equal variance. We can also do paired sample t-test by adding the paired equals true argument. And if you want to not use Welch's t-test, you want to assume equal variances, you can call the var.equal argument equals true. And you can see the help page for the t-test function for more options. And so here we're going to be looking at whether the RESP variable differs, whether people are looking at questions about economics or about politics. And so this is one of our key hypotheses. We assume that people would prefer algorithmic advice for economic questions, but not necessarily for politics questions. And so to run this test, we can use the formula syntax, which is a common thing that we'll be seeing in a lot of examples that we're doing. So here, the formula syntax has the dependent variable to the left of the tilde and the independent variables to the right of the tilde. And then note that we always specify the data separately as a separate argument. So here I'm just doing comma and then my data set, and this gives us a t-test output. And so here we see that these results are significant, and we get the mean of the economics, the mean of the dependent variable for economics questions and the mean of the dependent variable for politics questions. And so we see it's much higher for economics than for politics. We can also do ANOVAs using the AOV function. So we compute the ANOVA with the AOV function, but then we report it with the capital A ANOVA function. And we'll look at that a little bit closer in a second. So we're going to use employment here as an example of a variable with more than 2 categories to demonstrate a one-way ANOVA. So we just do the same thing like we did with the t-test, where we use the formula syntax, except we're using AOV, and the syntax looks the same otherwise. And so to look at the results, we need to use the capital A ANOVA function like I mentioned. So in the default little a ANOVA function is used for a lot of different things. But when you call it on an AOV object, like we computed here, it only reports type 1 sums of squares, which is different from what most other software we use would be. And it's also not necessarily what we're interested in. To be consistent with SPSS and SAS, we want type 3 sums of squares, which can be called with the capital A ANOVA function. But one important thing is that there's a sort of funky feature of R where the default contrast settings for the capital A ANOVA function don't work quite right with type 3 sums of squares. So you need to actually set them to be orthogonal contrasts. You only need to do this once per session, and I'll show you how. It's not that important to understand exactly what that means here. We can also always get type 2 sums of squares, which will be slightly different than type 3, but will usually also be better than type 1. But to match with SAS and SPSS, first we set our default contrast with this options call. So you only have to do this once per session, and then you should be fine. If you want to do different types of contrasts, you can always play around with it later. But for calling the ANOVA table results, just run this first, and then you'll be good. So then we need the car package for the capital A ANOVA. So if you need to install a package, you can just run this install packages line. I commented it out with a £sign here because I already have it installed. Then to load it, we call library, and then so we load up car. And so now we have the capital A ANOVA function, and I call type equals 3 for type 3 sums of squares, and this is the result we get. So we see that the employee factor is not significant. For 2A ANOVA, we can use multiple different factors at once. So here we're going to look at both the domain and month factors, which were 2 of our factors of interest. Remember, domain is the subject of the events being forecasted, and month is how far into the future they look. So here I run a 2A ANOVA just the same way, using the plus sign to add the extra factor. And then I call the big A ANOVA on it to get my ANOVA table. And here we see domain is significant, but month is not. If we wanted to look at the interaction, we could use the star representing multiplication instead of the plus. And so note that if I do this, it also includes the lower order terms as well. So this calls the interaction, but then it also represents both domain and month separately. And you can see that down here in the ANOVA table. So we have each main effect as well as the interaction down here, and likewise the interaction is not significant. We can use the little ANOVA function for several things, and one of them is to compare nested models. So in this case, the version that doesn't have the interaction was AOV full, and the version that did was AOV INT. And so we can enter both of these into little ANOVA, and it'll give us a nested model comparison. And again, here we see that the difference is not significant. We can get the estimated marginal means of our outcome variable by the factor using the emeans function from the emeans package. So once again, you have to install emeans, the package, then load it up. And then it also has a function called emeans. And so you can call that on your AOV object and specify the factor that you want to marginalize by. So here we get the average value for the dependent variable for economics and for politics. And again, this is what we saw before in the t-test, but here we get standard errors and confidence intervals as well. And of course, we can marginalize over our interaction by adding the by argument here. So now we see the difference between economics and politics for both different month factors. So this is a way of getting the estimated means for our interaction in the two-way ANOVA. For regression, we are going to use the LM function. And in R, ANOVA is actually computed via the regression method using something like dummy variables. And the AOV function is just a wrapper for the LM function. They do essentially the same thing. You can do everything with the LM function if you prefer. So we can use this to expand our two-way ANOVA as a regression with more variables, essentially an ANCOVA. But we can just think of it like a regression here. And so here I use the LM function, and I'm using the two factors that I looked at before, as well as a continuous variable age. So this gives us a regression result. And once again, we can use the capital A ANOVA to get the ANOVA table. And here we see age is significant in addition to domain. And if we want to actually get the regression table with the beta coefficients, we can use the summary function on our regression object, and that will give us a full output, including R squared, as well as the coefficients, which are the estimate here for each variable, standard errors, and t-test.